I wanted to briefly make this video to kind of introduce the concepts of circular equations and elliptical equations. All of this is going to be done in Cartesian coordinates, so x, y coordinates. And I wanted to kind of just show you visuals in terms of Desmos. For what I have graphed here, I have a circle. It's centered at the origin, and it has a radius of 1. You can see this in the equation. So it's a little hard to tell, but this is the equation for a circle. I've got sliders that I've created here so I can move this equation. But essentially, you're probably somewhat familiar with the terms h and k when related to functions and transformations of functions. If you remember way back to your algebra days, h is the horizontal shift for a function. This is the same thing that's going to happen for a circle. So I've got h currently set to 0. If I go ahead though and I move it, if I move it to the right, it's going to move it to the right. If I move it to the left, it's going to move it to the left. This is because it's x minus h, right? So this, if I have h as positive 1, that would be x minus 1 inside that square. That is a horizontal shift to the left at 1. The same thing happens with k, which you might have remembered is the vertical shift of a function. If I move it up, it's going to go up. If I move it down, it's going to go down. This is going to be the same case for circular equations as it is for any other equation, actually, literally any other equation. These behave the same. It's really nice that it's uniform like that. Let's move it back to the center so I can show you what r does. So r, I'm using the letter r specifically here because r is the radius of this circle. So in the case of this, my radius is 1. I have a radius of 1. This is actually where unit circle comes from. This is actually the definition for a unit circle. It is a circle centered around the origin whose radius is 1. And from that, we've derived an entirely new set of units called radians. Because the radius is 1. It's the base unit, aka unit circle. So in case you were curious, that's where unit circle comes from. But if I were to increase this radius, let's say to 2, then my radius should increase to 2, right? In terms of this, it's proportional for that. Now in the equation, it's r squared. So we want to be careful when we're actually computing this. The equation is set to equal r squared, not r. But again, it's a direct relation. If I make the circle smaller than 1, going to be less than that, and it negative because it's squared, it just kind of flips on itself, so don't really have negative radius. Technically you can, but we're not going to get into the polar functions in terms of that. But anyway, so that's just kind of how it relates to the circle and how we graph a circle. I'm going to now turn on our ellipse function here down at the bottom. Oh, I should probably have the radius set back because the radius is the radius for both of these. And currently right now I have it set, you're saying that looks exactly like a circle. The unit circle centered around the origin with radius 1. If I were to move h, does the same thing that it always does. If I were to move k, does the same thing it always does. If I were to increase r, it works the exact same way. So there's really nothing new in terms of what k, h, and r mean. For an ellipse, they mean the same thing they do for an ellipse and a circle. We have 2 new constant terms, though. You'll notice now I am dividing by fractions. And you can think of these are in terms of in the horizontal direction of my circle, how proportional is it to the vertical direction of my circle. So a is the constant underneath my x term. X is aligned in the horizontal direction. If I increase a, you'll notice I have a stretch or extended eccentricity is the term we call it in the x direction. This is kind of like x is being squashed as a fraction. If I change this, so I'm put a back to 1 when it's 1 that is just a circle. If I now increase b, b is under the y direction, I would expect a vertical stretch. So this is what we see. I have a vertical stretch. If I have the ratios the same, so let's create b and a to be equal, well, then I just get a circle. I get a circle that's a little different looking, but you can think I could factor out those terms and move it to the radius. So when a and b are the same, that's when I essentially have a circle. So it's kind of technically always been in the circle equation. We just don't write divided by 1 when it's there. We don't really need to. But the same thing can happen if I decrease b. or increase A lot, I get really, really stretched eccentricity, again, is the term that we're calling for.